Here, S how you actually store user-specific memories that persist across every conversation, even when they start fresh threads. We'll see the exact pattern for namespacing memories by user ID, creating unique memory entries, and storing them in a way that survives between sessions. The code shows how to extract the user identifier from the config, generate a new memory record, and persist it to a shared store that remains accessible no matter which thread the user starts next. Def update memora state, messages state config, runnable config * store, base store. Hash get the user id from the config. User id config configurable, user ID. Hash namespace the memory. Namespace equals user id, memories. Hash, analyze conversation and create a new memory. Hash create a new memory ID. Memory id struid, UUID 4. Hash we create a new memory. Store put namespace memory id memory. This demonstrates the persistent memory pattern for maintaining user-specific context across multiple interaction threads. The concept separates ephemeral conversation state managed by checkpointers from durable user memories handled by a dedicated store, creating a two-layer persistent system. What makes this distinctive is the namespace isolation, where memories are scoped to individual users but remain accessible across all their conversation threads. The pattern works by decoupling thread-specific execution state from cross-thread user context. Checkpointers handle the linear progression of individual conversations, while the store provides a key-value interface for memories that persist beyond any single interaction. This separation enables semantic search across historical memories while keeping conversation flows stateless and replayable. The design follows the principle of orthogonal persistence, where different data life cycles are managed by specialized components. This approach solves the problem of context fragmentation in multi-session systems. Without it, you'd need to either pass all historical context through each thread bloating state or lose continuity between conversations. The trade-off is additional infrastructure complexity, but the benefit is true memory persistence that works across restarts, thread forks, and time travel debugging scenarios. It's particularly valuable for assistant applications where user preferences and historical context should inform interactions regardless of which conversation thread is active. Let's break it down line by line. Def update memora state, messages state config, runnable config * store, base store. This defines the update memory function that persists conversation memories to storage. The store parameter uses keyword-only syntax to enforce explicit passing, preventing accidental positional arguments. This pattern ensures clean separation between state, configuration, and storage operations. Hash get the user id from the config. User id config configurable, user ID. Extracts the user identifier from the configurable runtime settings. This ensures memory operations are scoped to the correct user, preventing data leakage between sessions. Hash namespace the memory. Namespace equals user id, memories. This creates a composite namespace key using the user ID and a fixed memories string. The tuple structure ensures memory entries are scoped to individual users while maintaining a consistent category identifier, preventing collisions across different data types. Hash, analyze conversation and create a new memory. Hash create a new memory ID. Memory id struid, UUID 4. Generates a unique identifier for each memory entry using UUID 4. This ensures globally unique IDs, preventing collisions when storing multiple memories per user. Hash we create a new memory. Store put namespace memory id memory. This code persists a memory to storage with a user-specific namespace, USERID, memories, and UUID key. But unlike the official examples, it wraps the actual memory content in an extra dictionary layer under the memory key, e.g., memory, food preference. And instead of just food preference, the storeput call stores this nested structure as the value payload. Memory persistence pattern. The update memory function demonstrates LangGraph's approach to user-specific memory storage, where each memory entry is namespaced by USERID and assigned a unique UUID. The namespace tuple structure, USERID, memories must remain consistent across all store operations, or queries will silently fail to retrieve related memories. This pattern enables persistent, thread-independent memory that follows the user rather than the conversation session.
The store that holds nothing becomes the only home for what was never stored.